all right. It's super unclear what all is going to get captured. I'll try to repeat questions and things like that that happen in person for the recording on Zoom. But we are in our third class here. This is week 2 of the Undergraduate Radio Lab in 2022. I hope everybody is staying safe out there. It's I think there's some encouraging signs that the Omicron peak has happened potentially, and we're on the way back down. But I know lots of people who are testing positive these days, and I've got 3 kids in various schools, and I get about 5 emails a day about potential exposures. We've all stayed healthy, knock on wood, so far, but I know it's kind of crazy out there. I'm wearing good masks for you guys. I hope you guys are also staying safe. Obviously, you test positive, stay home. We're going to continue to do these lectures on Zoom. You can participate on Zoom. I encourage you to use everything that we got available to try to make it through what we got here. I know it's not ideal. We'll muddle through one way or another. Similarly, if for some reason I happen to test positive, right, I'm going to be giving a full remote lecture. I am doing my best to preserve to keep safe, but with 3 kids in public school, there's only so much I have control over. Great. So let me talk a little bit about some practicalities. So hopefully you all have your groups together. I think by the end of last Thursday, I think we had just about everybody in a group. If you're not in a group, you should let me or Christian know, and we can get you into one. I'm not sure if everybody has managed to get a little lab time here yet and try to get things started. If you haven't, you've got about 48 hours, slightly less than 48 hours to get that done. Remember, on Thursday, we're going to have you all do presentations. I might have a little content that I add to the end of it, but the first and major thing that we'd like to do is to have all of you present a little bit on what you've managed to achieve in the first week or week and a half of this class. Just in terms of a little guidance, so we are running with a bit of a larger than usual class this semester. Usually we have around 20. It seems like we have about 25 or 26 now. Occasionally people drop right before the first lab report, so it's possible will decrease a little bit. I hope not. I hope you all could stay in it, but I do understand it's a ton of work. That means in terms of presenting time, we don't have a ton of time in order to get through everybody, right? So we're going to try to keep it to like 2 minutes a person. It's not a ton of time, right? 2 minutes a person with a little transition time is going to get us through about, it's going to be an hour and 20 minutes or so of class. So I'm going to keep a timer. I'm not going to be like mean about it, but it is just good to have a reminder of what the time is. I'm going to start a little timer so that you can talk. I would aim, if you can, for about a minute or a minute and a half of you actually talking. And then the hope is that you have like a little something that I can offer a little feedback on, like a question, like, is this the signal I'm supposed to be seeing? Or why is there this weird glitch in the signal that I just got the other day? If you can, if you have a little something like that, then I can have an opportunity to try to clarify for that, both for your benefit and for the benefit of everybody in the class who may have seen a similar thing in their thing and not have a clue what it meant, or didn't even think to look under the hood of that and see like, oh, that was a weird thing. So Thursday's a great opportunity. Let me just run you through a couple principles of what a good presentation looks like. So the first key to a good presentation is do the lab. As obvious as that may sound, spend a little time, have read through it, have tried to acquire some data. I'm not demanding that you have perfect data or anything like that. when you come into this presentation, it's perfectly acceptable to present where you're at in the lab. And that could be, I tried to do this thing and I got in the way of, this thing and this thing got in my way. Or it could be, I spent the whole time trying to figure out how to get my bash RC file installed the right way so that I can source my Python environment, which that applies to you, I have to say this happens every year to almost half the class, really. So the fact that it happens is not a surprise. So anyway, it's fine to present where you're at. The goal, though, is to make good use of that time in terms of getting some feedback and capturing some things that you think might be useful to other people in the class. I suggest that you coordinate your content between your group. So we'll call you up as a group. Your group can decide whether you'd like to go first or you'd like to go last. A lot of people like to go last because it gives them a little more time to kind of see the lay of the land before they present. But the cost of going last is that lots of people already presented this thing, and then you have to go last and say the same thing. People don't like doing that. So if you go first, then it takes a little extra bravery, but then you have the added benefit that nobody already presented what you were going to say, which is, anyway, I can see arguments there either way, but within your group, decide when you want to go. We can't promise that we'll go in an order, but you're welcome to request an order. And try to coordinate so that each of you in the group are talking about something different. So we're not going to coordinate between different groups, but within your group, if you can say, somebody was focusing on hooking up the cables and making sure that was all right, then you can talk about some of the things that you found there. Maybe you found that, the oscilloscope is not giving you the same amplitude that you thought you should have been seeing coming out of the function generator. Welcome to talk about things like that. Maybe somebody was writing the little Python script that was acquiring the data. You can talk a little bit about how you did that, what your script looks like, things like that. If you can make some plots of it, maybe somebody can talk about here's an example of what we were thinking of showing for the Nyquist aliasing kind of thing. Those are the kinds of things that would be kind of good divisions on this. And as we get closer to when the lab is due, it's increasingly a good opportunity to use these presentations to try out a plot, try out something that you think might be a plot or a paragraph that you'd like to put in your report, and just bounce it off me and see, is this in the right area? Do you have, is there something obviously wrong with this that I need to fix for the report? So these are opportunities to get feedback like that. Despite the fact that I'm here listening and may offer you feedback, though, you should be presenting to each other. Your target audience is your fellow classmates, right? So, don't be afraid to kind of take it from the top. This is what we learned, and this is kind of my understanding of it. Things that work for you, help you understand, help you, how are you organizing your code? How are you, what kind of plots are you thinking about? These are just good things to talk to your peers about and hear what other people are thinking. And it just helps you write your own report better and have a better understanding. So your target audience is each other, even though I'm here listening and offering feedback. It is perfectly okay, though, to have in your presentation some, like a direct question to me, so you end with, all right, so we got this plot and there's a spike here that I don't even understand what that means. What do you think, kind of thing. Any questions? I think that's it. Yeah. Yes, sorry, thank you for clarifying that. Yeah, so part of the presentation should be a visual aid. That could be a PowerPoint slide that you have prepared. If you are preparing PowerPoint slides, then my suggestion is that you collate those slides so that one member of your group is presenting them, or you could send them in a bundle and I could present it on my laptop. Either way is fine. But it'll save us time switching slide decks if you can bundle your whole group's presentations into slides. If, on the other hand, sometimes it's more helpful to just do a straight up share screen and jump into a Jupyter notebook that you're working on, or to like, here's the text file that I was using to acquire the data kind of thing. So you're welcome to do any of that. It can be a shared desktop, it can be a slide, whatever it is, but you should have a visual. It could even be a visual aid, could be a setup if you want. But be aware that if multiple groups want to use the same setup, you're going to kind of be arm wrestling over who does the thing. But a nice little prop is a fine thing to have as well. Another question.
How much allocated time was there?
So it's basically 2 minutes per person, and I would suggest going on the short side of that, an hour, a minute and a half per person, just to allow a little time for feedback. Another thing I can urge you to do is to practice. It's a short thing. You can talk it out loud. It feels a little weird if you haven't presented in person before. It feels a little weird to talk in front of people. It feels even weirder to talk to yourself, pretending that you're in front of people. But it's just a thing that you got to practice. Public speaking is a skill just like any other thing, and you get better at it with practice. Be aware that it takes longer to say a thing than you think it takes to say a thing. One of the rules I've heard is that, if you're giving a presentation, a slide per minute is about the max that you can go. So if you're presenting for a minute and a half, you're basically talking about a slide per person, maybe 2, right? So don't go like super dense and then discover that you couldn't say half of what you meant to say in your presentation. All right, remember to breathe. Remember, it's going to be fine. It's just, it's just capturing where you guys are. And don't be afraid to have a little fun with it. Sometimes people do funny, hilarious things. Some of the meme stuff that you see around the room here are things that came from a group presentation of people incorporating memes, took some video. There was a great video of one of our GSIs repairing a dish because we have a little webcam on the dish over the hill, and some people were spying on him while he was fixing the dish and like turned it into like a little video. It was hilarious. Anyway, lots of fun stuff you can do. Have some fun with it. All right. Any other questions about presentations? Cool. And also, as always, be good audiences to each other. Okay. Let's dive back into course content. So I'm going to share my screen here so that we can write. And when I'm in share screen mode, I'm not good about seeing comments. So Christian's gonna give me the assist on if you typing comments. All right. So. Let's see where we started. So just a quick recap of last week. So we delved into a lot of, kind of practicalities of getting into the lab, stuff like that. But once we got into actual content, we talked about the, green is a bold color, maybe not the one I want here. Okay, the Nyquist criterion. Anybody remember what the Nyquist criterion was? Yeah, Ketzel?
It's how you make sure that you're showing the, it's minimum number of, like, I guess, takes per sine wave to make sure you're getting the accurate sine wave and not a broad period.
That's right. And what is the number of samples that we want?
2 per the period.
Yeah, you need greater than or equal to 2 samples per period. Otherwise, what happens?
If you have less than that, you won't necessarily be able to tell what direction the wave is moving in.
That's right. And we had a specific word for that. Yeah, aliasing. Otherwise, we alias. I just want to reemphasize that aliasing isn't always bad. You can actually use it to, for example, represents a sine wave that you know is a higher frequency, but you can still get the amplitude, the phase information, all this interesting stuff from it by aliasing it on purpose if you wanted to. But you should be particularly careful about when signals stack on top of each other. And for understanding when signals stack on top of each other, we had this idea of windows, right? So that if this is the frequency axis, and this was maybe power, then if you had a spectrum, I think I drew it kind of like this. Then there's a boundary here. This boundary is where this Nyquist criterion here is, which is the sample frequency over 2. And then things alias around backwards into this. But each of these are what we call Nyquist zones. This would be 3 times new sample over 2. And so each of these are Nyquist zones. So this is number 1, number 2, number 3, and so on. And what you want to really be careful about when you're putting in a signal into a sampler is you need to make sure that you don't have frequency content in that signal that straddles these boundaries, right? Because the problem is if I put in a signal, let's say this red signal, and suppose it straddled 2 boundaries, suppose it went like this, then this half of it, this upper half of it is going to alias back down, and I'm going to get a stacked spectrum here that would go like this, that has, neither of those were very good drawings. Let's try again. You'd have a stacked spectrum that has information from both sides stacked on top of each other, right? And that's kind of a problematic thing because now you're mixing together different signals from different frequencies and they're literally on top of each other. It makes it very hard to understand what you've got. So you got to, the most important part of the Nyquist criterion is to ensure that you don't smush signals on top of each other. So be careful about where you position the Nyquist boundaries, and be careful to filter your signal going in so that it doesn't straddle those boundaries. So for example, if you had a 100 megahertz sample clock, then you're going to have a 50 megahertz Nyquist criterion. 50 megahertz would be your maximum frequency at which this first aliasing happens. So you could use, for example, a filter that filters from 0 to 50 megahertz. That would be fine. But if you did filter from 0 to 75 megahertz, that would not be fine because the upper 25 megahertz of that would jump back down and stack on top of the lower. So that's an example. If all you had was a 75 megahertz filter, then you need to think about tuning your sample frequency up to something like 150 megahertz in order to get it to come through. That's the kind of math that you end up doing here. Is you can either select what your filtering of your signal is, or you can select what your sample frequency is. You just need to make sure they're compatible one way or the other. All right, so that was sampling. We then went on to talk about Fourier transforms. Sorry. So with Fourier transforms, we had the analytic, like the true Fourier transform. That true Fourier transform was if I have an f of t, a function, then I could integrate it against a complex sinusoid. And as part of this, we'll just remind ourselves that sinusoids, the true sinusoid is a complex e to the I omega t kind of thing. Because that is the only sinusoid that is truly one frequency. If we respect that we can have both positive and negative frequencies, the only one that is truly just one spike in Fourier domain is a complex sinusoid e to the I omega t. If you have only like the sine or only the cosine, then you actually have 2 spikes, one at a positive frequency and one at a negative frequency. So we can take a Fourier transform by integrating this in time, technically from minus infinity to infinity, to get a Fourier coefficient, which we write as like a little tilde above our f as a function of frequency. And then we can undo that with an inverse Fourier transform and get back to our original f of t by integrating up our Fourier components with the reverse sinusoid. And then we turn these into discrete Fourier transforms by discretizing the time. So instead of having a continuous time variable with a dt, we can have a discrete time, a t1, t2, t3, with a delta t in between them. And the result of that was that for a given delta t, we could relate that to a total bandwidth of the signal we put in. And for a delta nu, which is a resolution and frequency, we could relate that to a total time over which we looked at a signal. So the resolution and time that I give you in one domain determines the bandwidth and frequency that I can have in the Fourier transform. And that, in some ways, is saying the same thing as the Nyquist criterion, right? It's saying that if I have a certain sample frequency, the faster the sample frequency, the more time samples I get, the wider a bandwidth I can represent in my Fourier transform. That makes sense. That is basically the Nyquist criterion. And it works the opposite direction too, that the resolution I have in frequency domain determines the total time interval over which I need to represent that signal. Or flip the other way, if I want good frequency resolution in my spectrum to see all these little structures in frequency, I need to look at a long time interval in order to get that information out. So there's this inverse relationship between time structure, the width of time structures, and the width of frequency structures. And we're going to delve into that a little bit more today with a thing called the convolution theorem. All right, let's so let's get started with the convolution theorem here. That's what we're going to do today. So I'm going to start kind of abstract mathy with you, and then I'm going to try to bring it into a very kind of visceral feeling that you can have for what a convolution or a correlation is and what it means. So let's start off with the definition of a convolution. All right. A convolution is a thing that you do with two functions. You take two functions and you convolve them together. And what you do when you convolve them together is if you have an f of t and you have a g of t, these are the two functions, then I'm going to convolve them together. And this is what a convolution is. I will say f convolved, and I'll use this kind of weird star symbol to mean convolve. F convolved with g is a function of a new variable called tau, which is the shift between the two functions. And it is equal to this integral of f of t multiplied by g of tau minus t dt, integrated from minus infinity to infinity. All right, so this is the definition of a convolution. And there's a very related thing. We'll get into a second, like what the heck that means. There's a very related thing called a correlation. So I could do the ditto for correlation. It's almost the same thing. And I'm telling you what it is right now because I occasionally slip up and call one the other, and vice versa. So I might as well show you both so that if I slip up, it makes sense. And I will try to use an actual 5-pointed star for the correlation as opposed to a 6-pointed asterisk for the convolution. They are almost the same thing, except for when I do this integral right here, I do a conjugation of this, in case it's a complex function. I do a conjugation of it, and I run the time the other direction. Okay, these are very close to the same thing. One is a slight difference, which is that for the correlation, it basically flips by conjugating and flipping the time around, it deals with complex functions better in a way that does squaring the way that you'd think that a complex function should square. All right, so let's understand intuitively what this means right here. A convolution is taking two functions, okay? The second function, it's running time backwards for it, right? So it flips it around. See, there's a minus sign on that time. And then you give me a value of tau, and that is a shift between the two functions. It's sliding one past the other for a given tau. And for each different tau that I want to try, it multiplies the two functions together and integrates them up to say how much do they overlap. Okay? It's even easier to see what's happening with the correlation, which is why I had to go straight for the correlation here. For a correlation, it's taking two functions without any flip, two functions, sliding one past the other by a factor of tau, and multiplying them when they overlap and integrating that up. So you could imagine, suppose f of t is just like this random noise thing going up and down. Suppose it just goes zig, zig, zig. If I take that function and if I correlate it with that exact same function, this is truly noise, then when I shift it, nothing's going to line up, right? Because it's just random noise, right? So if I take that and I copy it, make an exact copy of it and slide it over, if I slide it over some amount, it's not going to overlap. It basically integrates to zero because the noise over here has nothing to do with the noise anywhere else. But when I overlap it at just the right thing where they perfectly line up, then everything squares, right? When everything squares, then when I integrate it up, I'm going to get a large number, right? That's called if you do that with the same function, it's called an autocorrelation. And it's a way of measuring how much power is in your signal. And I'm going to tell you a couple other cool things about the autocorrelation once we kind of build our intuition for what a correlation or a convolution is.
Why would shifting it nullify it? Wouldn't it just make a different noise if it's truly random?
Yeah, so it makes a different noise when you multiply. So you shift it over, it's kind of just a different noise. You multiply one by the other, it's also just a different noise. But then the key other ingredient is you integrate over it, right? And when you integrate up noise, it's going to integrate to zero because for every positive fluctuation you got somewhere, you got a negative fluctuation somewhere. And that whole thing is going to average up to nothing. That's the key ingredient. Okay, so let's see for a second if we can we just got to build some intuition here. So let's start with correlation. Correlation, I feel like, is a little more intuitive. It uses the star, and all you got to do is remember to conjugate. If it's a complex number, you just got to remember to conjugate the second one. All right. Yeah. Question online?
Yeah, there's a question. G is shifted by tau or star G.
Yeah, so this this little minus tau here means that if you want to evaluate G at the same number, like suppose I did this at time 3 and I want to say, how do I get time 3 here? Well, if this tau is 1, then my T is going to have to be 4 to make 4 minus 1 is 3, right? So to evaluate G at that same value, whatever T does, whatever tau does, my T has to slide to compensate for it. So that's how you can kind of see that a tau is sliding your G function along the time axis. It's a time shift. You could think of tau as a delay. Okay, so let's see if we can, in our brains, try to do a correlation. Suppose I've got an f of t that is this thing. I'm going to try to draw something here. It's going to go like that, and then it's going to go over here, and then it's going to wiggle fast, like that. And suppose I have a g of t that looks similar, but I'm going to put them closer together. They go like this, and then they go. Okay, these are my two functions. I'm leaving up here what a correlation is. My question is, what is f star g as a function of tau? Okay, and I'm going to give you 4 options. If you're online, I'm going to do an online quiz that you can fill out a form for. If you're in person, you're going to have to make hand signals. You're going to have to go A, B, C, or D. Are we cool with that? Or should we just do 1, 2, 3, 4? All right. All right. We will not do the American Standard Sign Language letters. We will instead do 1, 2, 3, 4. Okay. So option A, I'll give you here, goes like this. It goes wiggle, wiggle, squiggle, squiggle. Option B is spike, spike. Option C is ones, then zeros, then ones, then zeros again. And option D is a big flat 0. So those are A, B, C, and D. Think for just a second here. I'm going to put on my poll, which I will now launch if you're online, so you can answer there. Do it just, you know, you didn't memorize the answers instantaneously. There we go. Oh, and I guess you guys get to see my version of the poll if you're in the class. Maybe I should be hiding this over here so you can't see it. Oh, now it's changed. Oh, can't win. Can't win. I also can't grab it anymore. There we go. Okay. Let's take a shot at it. Can you hold up what you think? A, B, C, or D? Or 1, 2, 1, 2, 3, or 4? Got some ones, some twos, some threes, a 4, a split vote. And we also have I would say a full representation online, which I'm going to end right here. Full representation online with maybe a bit of a preference for option B. Okay, so now that you've had to think on your own, let's walk through this together. So remember, for this correlation, what we're doing is we're taking one and we're sliding it by the other and then we're trying to measure what happens. So let's start with them in different positions here. Let's start with f of t. I wonder, I might be able to just do this. This is one of the, can't do this on the board, but copy, edit, paste as a new layer. Oh, check this out. Check this out. Ha! Oh, no, come on. Come on. Let me do my magical select. And ha, okay, now we can do it. Okay, had to get my transparency set up here. Okay, here we are. We can convolve these things, right? So if I start off with G over here, this would be a large negative tau. Right, so it requires a large negative time to undo. G is over here. When I multiply these, nothing is overlapping. The zeros of G are overlapping all the signal parts of F and vice versa, right? So if I multiply these right now in this position, it's just 0 across the board, okay? So I know that whatever I've got has to be zeros on the far left and zeros probably on the far right when I do the same thing over this way. Was there a question?
Yeah, there's a question. Are we talking about convolution or correlation?
See, I did. Okay, so I am talking about a correlation. I warned you that I was going to immediately start interchanging these words. We are correlating. We're following the mathematical framework that is on the screen right now. And the reason I keep messing them up is because they are doing basically the same thing. So I've almost treat them as synonymous in my brain. Okay, so we start all the way over here at a large negative tau, and we get 0. What happens when I get to like this point? So I've got a big fast squiggle going over the sine wave, right? And when I multiply these, some parts are going to go positive and some parts are going to go negative, right? But they aren't aligned. And as a result, this is the same result that you get if you multiply 2 sine waves of different frequencies and then try to integrate it up. And the answer is that they integrate to 0. Because one of them is changing the sign of the other even midstream, but it's all symmetric. So for every positive going part, you just go to the other half of it, and there's always a corresponding negative part to it. So it's going to integrate up to 0, even when these parts overlap. Now let's go a little further over. What happens here? Well, this fast squiggle, both fast squiggles are being multiplied by 0, so they don't factor into it at all. But this slower squiggle is now lined up with the other slower squiggle, right? So when I multiply those two together, it's going to square that. I'm going to see 2 positive going lumps. And when I integrate that whole thing up, this part over here will integrate to a value that is not 0, whereas everything else will have been 0. So, so that means when these things line up here, it's negative. Or sorry, it's some fixed value. What about over here? 0, right? Nothing overlaps. And what if I go further over here? All right, so now we're illustrating how lousy of an illustrator I am. But these squiggles were supposed to be the same squiggle. And maybe they are. If they were the same squiggle, then the same argument as before applies, right? Which is that they square, and you get a net positive value here, right? So you should get another positive value, and then nothing here, right? Because this is the same argument as before, multiplying 2 different sine waves integrates to 0. And then over here, 0 again. So I think by that argument, it can't be A and it can't be D, right? So it's either B or C. And it kind of depends on what I meant by these spikes here. This technically might be a net negative value here, where there's a downgoing lobe times an upgoing lobe, and everything else is 0. So it really depends on how I, all right, I want you to go away now later. There we go. It really kind of depends on exactly how I drew it, but in this case, I'm going to go with option B, that we have these spikes here. Let me draw. And it might be that these spikes needed to be a little more select, and then there we go. Let me draw again, please. Thank you. There might be a little negative blip here. It might look a little bit like that. But there are two distinct regions where they overlap and zeros elsewhere. So we're going option B. Okay, so that was a little bit challenging. It would be nice if we had a cool little Jupyter notebook where we could just interact with these things. And guess what? We do. I made you one. Now I just have to find it. And I think, is it down here? No. Sorry. Let me find my, where'd it go? Here we go. Got it. Okay, so so here we are doing convolutions and correlations. In this notebook, it's mostly correlations, and it's just implementing a convolution here. Let me run the cell really quick here. So here are two different functions. In this case, f is this big sine wave, and g is now this square. And the product of the two at any moment is illustrated by the shaded region in this notebook. And then down at the bottom, let me zoom out just a little bit. There we go. Down at the bottom, we can control tau. Okay, so I can slide one with respect to the other. And you can see at different places, different taus, the shaded region can be negative like it is over here. It can be crossing so that I have as much negative as positive, which should integrate up to 0 over here. And then it can be net positive over here. And you'll see down at the bottom here on the bottom panel is that result. It's the integral of them. So you can see as you slide back and forth in delay, you're sampling out a new function, a function of delay, and the value at each point in that function is what you get when you multiply the red curve times the blue curve and integrate up the area underneath that. Yeah.
I'm wondering if you just have convolutions and correlations to do the same thing. I understand how correlations work, but convolution, the lower t is the one that's being subtracted. So how does that?
Yeah, so in convolution, the time runs the other direction. So you can think of it as flipping your function around back the other way. And for some reason, my brain has a hard time with that. So I much prefer the correlation version where I don't have to do that flip in my head. Correlations work better for me because they square a function, which is a thing that feels like I understand it. Whereas multiplying a function times something that is not like if it's complex, it's not doing the conjugate. So it's like some new complex number, which I find a little hard to get my head around, which is why I keep wanting to talk about correlations, even though what we usually talk about is called the convolution theorem. All right, so this is kind of fun. You're welcome to play with this. This is in your Jupyter, in your UG Radio repository under Jupyter Notebooks for Lab 1. This one's called Convolutions and Correlations. You're welcome to interact with it, play with it. You're also welcome, you can actually change the definition of F and G if you want to, just by editing a little Python code here. And I'll do the same thing for any functions that you want to do and draw up here. So it can be kind of fun. All right, so a thing that, in fact, what if I change G here? No, actually, I like G. I'm going to change F. I'll change F to, let's see, is this, yeah, this is Vim, thank goodness. All right, so I'm gonna change F to something kind of like G. It's going to be a square function where I'm going to have a slightly different width, like maybe 0.5, width of 0.5, where it'll be 1, otherwise 0. So then I have this other function here, and I can also slide it back and forth. You can see here, when I do two square wave functions, when they don't overlap, it's 0. When they start to overlap, then I start getting some positive value, and it increases as they overlap more and more until when the blue is sitting completely inside the red, it's at a maximum value. And then it's not really, that value is not sensitive on where exactly the red is centered, right? It's still, the product is still 1. And then when I go off the other end, it slants down. So, question? What is this used for? Okay, yeah. This was what I was just about to do, which is why I wanted to do this example. So great question. What is this useful for? Why the hell would you want to do this? Number one is, if you look at what this is doing, and you squint a little bit, you can kind of convince yourself that what I'm doing is smearing out one function by another function. Especially when they're like squares like this, then I'm kind of smearing it out. If I were using two Gaussians, then it would be even more clear. One is, I would get a new thing that is smeared out, a smeared out even fatter version of what I had originally. So if you guys have ever played around on like Photoshop, or GIMP is what I'm using to write on here, you'll actually see, you'll go to like filters and you say like Gaussian blur. What is that Gaussian blur doing? It is convolving your image by a Gaussian, for example. So blurring is what a convolution is doing. It blurs or smears. It takes power from one place and it smears it out. So that's one thing that it's used for. Correlations kind of do a related thing. They do almost the same thing, except for because they square a function, I can draw a very rough, like noisy function. And if I convolve it with itself, I'll get some other new weird crazy thing. But if I correlate it, it will literally be 0 except where it squares. Where it squares, it spikes up to a value. So correlation does kind of the same thing, but what it's really good is finding where two things match. They match up, which kind of corresponds to how we use correlation in English, right? We use it to mean like when two things are correlated, then they move together, right? And correlation, when you do a correlation, you're trying to find like a little copy of function G inside of function F. And if they ever line up, then it squares and you get some power there. So those are like some hand-wavy ways of using it, but it turns out there's even a more powerful way of using a convolution. And it's the reason why I have to talk about it in this class. It is not optional. Might be optional to do a Gaussian blur on an image, but it is not optional to learn about convolution. And here is why. Let's remember what a Fourier transform is, okay? I'm just gonna copy, maybe I actually had it here already. The Fourier transform, it's right up here, okay? And then I have the definition of a convolution right down here. Now I'm going to do something kind of crazy here. I'm going to plug in the definition of the Fourier transform into the convolution just to see what happens. Okay? Guys with me? Fourier transforms are real things. I can absolutely represent, actually, I guess I would use this one over here. I can absolutely represent a function as the integral of its frequency coefficients. So I'm going to do that, and I'm just going to substitute it out right down there. Okay, so I'm going to start off with f of t, remember, is equal to the integral, and I think there's technically a 1 over 2 pi in this one that I forgot to write down before, of f tilde of w, or omega e to the, and there's no minus on this one, I omega t. So that means if I take f convolved, and this time I do mean convolved with this kind of star, g, as a function of tau, which remember was the integral from minus infinity to infinity, f of t, g of tau minus t, dt. And this was integral dt. Okay, so I'm just going to do the substitution here. So I get, this is equal to an integral of the integral of f tilde of omega, sorry, this was d omega, d omega, sorry, I'm forgetting my e to the I omega t, d omega, I'm going to do omega 1 here because I'm going to have to do a second integral of the g, and those omegas aren't necessarily the same omega, they're two different integrals, right? So I'm going to do the g over here, g tilde of omega, e to the I omega, sorry, this is omega 2, but remember, this isn't t I'm putting here, because this is g of tau minus t. So wherever I was going to use t, I have to now instead use tau minus t, right? Tau minus t. D omega 2, sorry. And then that whole thing is dt for this bigger integral that I did, okay? Now, because I labeled all these frequencies separately, I can actually move all my integrals off to the left-hand side here. So I'm just gonna go blah, integral, f tilde of omega 1, e to the I omega 1 t, g tilde of omega 2, e to the I omega 2, tau, and then I'm going to go ahead and just split this out and get an e to the minus omega 2 t. I'm just expanding this little sign thing, the subtraction inside the exponent. And then I have d omega 1, d omega 2, dt. All right. Now, I am going to bring this e and tuck it over here with this one. Okay, so I have blah, 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 integral. Sorry, just bear with me on this for just a second. E to the I omega 1 minus omega 2 t, g tilde, whoops. What was that? Oh, I was about to make a mistake. I'm undoing my mistake. E to the I omega 2 tau dt. I think I've, oh, and I think I forgot some 1 over 2 pi's squared. Okay. So what I'm about to do now is I'm going to integrate up this thing, dt. Okay, this is the only thing in the whole integral that has a t in it. So I can integrate up dt, and this is actually the definition of a delta function in these two frequencies. Yeah,
shouldn't you need to integrate the omegas before the t, so some sort of non-linearly combined.
Sorry, no, so integrals I can do in any order.
Okay.
I'm allowed to. They are linear operators is the key function of the key attribute of integrals that allow you to do them in any order. And sorry, I did drop these differential pieces. So I haven't integrated over these yet. I'm just choosing to integrate up my t first. And if I do my t first, I can integrate over t. The only thing in here that involves t at all is this e to the I omega t. And sine waves only integrate to something other than 0 when it's a 0 frequency sine wave, which means that this thing will only be non-zero in this integral when omega 1 is equal to omega 2. And that's a thing that we call a delta function. So I can remove, mathematically, it's that e to the I omega t, the integral of that dt is equal to a delta function in omega, and it just by Fourier transform rules, it has a 2 pi embedded in it. So what's going to happen here is that I get a 1 over 2 pi that survives here. I can remove one of my integrals. I get an f tilde of omega, I say f and write g, an f tilde of omega 1, a g tilde of omega. Well, this thing became a delta function in omega 1 minus omega 2, which means it's 0 everywhere except where omega 1 is equal to omega 2, which means I can treat omega 2 as being omega 1 because it's the only place where this has any value. So I locked my two omegas together. So now everything in it is an omega 1. All right. So the upshot of this whole thing is that if I convolved two functions here, I convolve, this is just a convolution, then in the Fourier domain, which is what I'm in here, you'll see that this, if I rename this tau t, this is a Fourier transform, right? It's a Fourier transform of the product of these two things. This is the Fourier transform of the product of f tilde with g tilde. So if I convolve two functions here, so remember, this was f star g as a function of tilde. If I take the Fourier transform of that thing, I'm going to get on this side f tilde of omega times g tilde of omega. Yeah, question.
Didn't we start this with the inverse Fourier transform?
We did start this with the inverse Fourier transform. And then this whole thing turned into an inverse Fourier transform. And now I guess I have a positive I here. You're right. This should be an inverse Fourier transform. If I take the inverse Fourier transform of, no, it should be a direct Fourier transform, because if I now substitute this into here, and I should have lost one of my integral symbols here. I lost one from integrating the t, and I lost the other from integrating against omega 1 that locked it, omega 2 that locked it to omega 1. So this Fourier transform, if I plug this in here, then if I did a forward Fourier transform, then it would be a double integral of f of I think I'm not going to go through this. I think I can show you pretty straightforwardly. Remember, we can apply if we apply a Fourier transform and then apply the inverse Fourier transform, it undoes it and gets you back, right? We can recognize that this down here looks like an inverse Fourier transform of this thing. It's this thing integrated by an e to the I omega something d omega, right? So if I do the Fourier transform of this thing, it's going to undo it, which means that if I do the Fourier transform of this convolution of these two functions, it is equal to the product of the Fourier transforms of those two functions. So if you zoned out and didn't like all this math, let me give you the upshot here. The upshot is when you convolve two functions, you multiply their Fourier transforms. Convolving is multiplying Fourier transforms. And similarly, if I multiply two functions, I convolve their Fourier transforms. These are two statements of the same thing. I'm writing it right here. If I convolve two functions, I multiply their Fourier transforms. If I multiply two functions, I convolve their Fourier transforms. Right? This is the same statement as the above, just recognizing that I can do I can start in any domain. I can start in frequency domain or I can start in time domain. Either way, if I regard these as the two functions that I'm multiplying, then what I did was I convolved their Fourier transforms. If I regard these as the two functions I convolved, then I multiplied their Fourier transforms. Works in either direction. Why the hell would you want to multiply Fourier transforms in the first place? I'll tell you. You want to filter something and get rid of some frequencies, right? We would love to do that. How do you do that? You convolve. That's how you do it. That's why we bother doing this. Yeah.
So you're saying, so when you say multiplying functions together, the same involving the Fourier transform, like in an interval, basically, does that mean that basically every all the equations we use in any physics that we derive in any other class, just you can think of it as all as convolution to some degree. Like any other convolution, when you think about it, like when you do all your math derivations that involve calculus.
Anytime you multiply two functions, you could have written it as a convolution of their Fourier transforms. This is like there wasn't physics here. This was just math. This is pure math, a pure math result. We're going to use this pure math result in order to do some physics. But yeah, there's no way around it. If you multiply two things, you convolve their Fourier transforms. If you convolve two things, you multiply their Fourier transforms.
Is there a correlation version of this?
Is there a correlation? Oh yeah, so this thing is called the convolution theorem. Convolution theorem. There is a correlation theorem that is essentially the same thing. The correlation theorem reads as that the Fourier transform of f correlated with g as a function of tau is equal to f tilde of omega times g tilde conjugate. There's where that conjugate came in the correlation as a function of omega. So if you just convolve, then you just multiplied the Fourier transforms. If you correlate, then you multiply, but you conjugate the second one. And the correlation theorem is particularly handy when G is just a copy of F. Because when G is a copy of F, then G tilde is the same thing as F tilde. Conjugated means that this squares it. So if you want to measure how much power, what the magnitude of the number is at a frequency, how much power did you get at that frequency, then the correlation is the thing that you want it to do. Okay, so we need to get our heads around this a little bit. We've seen it. I made some bold assertions. Let's try to get a feel for it intuitively, because it turns out that if you can embed correlations and convolutions in your brain, this class is going to be so much easier. I do this to the point that my grad students, like we occasionally do holiday skits, they make fun of me of actually just living in Fourier domain. That I just, I love Fourier domain. In some ways, it's so much better than real domain. Things are cleaner. Convolutions, ugly. Multiplication, way better. I much prefer living in Fourier domain. Okay, so let's do another one of these little questions, and I'll do a little online poll for those of you online here. Suppose I have a sine wave, convolved, so straight up convolved, not correlated, with a faster sine wave. Okay? What am I going to get? Am I going to get a faster sine wave sitting on top of the one like that? B, am I going to get a frequency that is kind of halfway in between? C, am I going to get two spikes? Or D, am I going to get 0? All right, think about that for a second. I'm going to launch the online poll. First, I have to get rid of this one. All right. And then I got to hide this from people who are spying on us in class. All right, think about it. We're convolving two sine waves of different frequencies. And the question is, what do you get? All right, about 10 more seconds. Get your answers in if you can. It's okay if you're wrong. We're just trying to figure this stuff out. All right, and let's see what we got here. So online, we've got a fairly even distribution, maybe a slight preference for D. In the classroom, I think we have a slightly higher preference for D, but also more, ones and twos. I don't see a 3 here. People didn't like my double spike here. Okay, so there are a few different ways of getting at the answer here, but I find the most easiest is to just remember that a convolution is multiplying Fourier transforms, right? What is the Fourier transform of a sine wave? Fourier transform of sine wave is equal to what? What's that? Sorry, my ears don't work very well. Delta function. Close, except for only for a complex sinusoid. 2 delta functions because it's a real value sine wave, because I can't draw complex data on a screen here. Yes, 2 delta functions. What is the Fourier transform of a faster frequency? 2 different delta functions that are maybe separated. If I convolve these 2 things, what do I do with their spectra? I multiply them. And if I multiply them when the spikes don't overlap, what do I get? 0. And that is why D is the correct answer. And we did that only using multiplication. We didn't have to use the fancy integrals with sliding things. All right. So if you can master the convolution theorem or the correlation theorem, if you can master that in your head, you never have to do an actual Fourier transform again in your life. You can just multiply. It's great. Okay. All right. What if I do a different one? More practice. What if I convolve there's a name for this kind of function. It's called a top hat. You can kind of see, right? It's a top hat, right? Top hat. We call it a top hat function. It's 0 everywhere except for over a certain interval here where it's 1. That's your top hat. Maybe I should buy myself a top hat just so I can wear it on the day that we talk about top hat functions. Suppose I convolve that with a delta function. What do I get then? I'll give you some options again. Option A is you get a sine wave over the interval where the top hat is not 0. Option B is you get a top hat that slid sideways. Option C is you get a sine wave that kind of grows like this. And option D is our good favorite, the flat line. All right, those are your 4 options. We're going to practice this again. And let me try to launch the, come on. There we go. All right, feel free to put in your answer. I'm going to hide you from the people in person so they can't spy. Everybody's thinking for themselves, convolving a top hat with a spike. All right. We have some answers. We're just kind of going through these. We're just trying some things. Sometimes one answer is not enough and you have to do 2. I guess if you want to split your vote. All right. Last chance online. Get your votes in. 4, 3, 2, 1. All right, we're ending the poll. All right, and online we have mild preference for B over A. In classroom, we have a preference for B with some C's in here. Cool, okay. Let me just talk for a second about Fourier transforms you can do in your head. There are a few Fourier transforms that if you can do it in your head will make your life easier. Then you can, again, avoid doing Fourier transforms in general. One Fourier transform that we've already talked about, the Fourier transform of a spike. So this we call a delta function. What is a delta function Fourier transform to? A sine, but we got to make sure that we do a complex sinusoid, right? So I'm going to draw both overlapping here, and we're going to say that this is e to the I omega t. All right, so delta functions, things that are very sharp, spike, Fourier transform to things that have infinite extent, right? If I ask how much power is in the sine wave, it's got power everywhere, right? If I square this complex sinusoid, it's got unity amplitude everywhere, right? So things that are very infinitely narrow, Fourier transform to things that are infinitely wide. That's a good Fourier transform to know. And of course, if you know it one way, you know it the other, right? Because Fourier transforms pair up. If I give you a complex sinusoid, you know its Fourier transform is a delta function. Another good one to know is that the Fourier transform of a top hat Anybody know this just off the top of their head? Yeah? It's a decaying sine wave. Yeah, it's got a funky name. It's called a sink function, but not with a K, because that would be a thing you get water out of in a kitchen. It's a sink. And technically, it's a sine x over x. And it's defined so that if x is 0, so a sine of 0 is 0 over 0 is 0. What is it? It's kind of an undefined. They define it at x equals 0 to be 1. And so what does this look like? It looks like a decaying sine wave like this, which was what I was trying to draw on option C. So if I just directly Fourier transform a top hat, I'll get a sink function. And the wider the top hat is, the thinner the sink function. The wider the sink function, the narrower the top hat is. Okay? So that's a set of Fourier transforms. There's really only one other one that I think you need to know. There is one function and only one function that is preserved under a Fourier transform. What was that? A Gaussian, that is correct. A Gaussian is the only function that is preserved under a Fourier transform, which is to say that a Gaussian that goes e to the minus t squared over 2 sigma squared will Fourier transform into another Gaussian. Oh, that's not a Gaussian. There we go. Where this is e to the minus omega squared over 2 1 over sigma squared. And that's just to make explicit that the widths are inverse, same as everything that we've talked about. The narrower you make the time one, the fatter the frequency one is, and vice versa. The narrower the frequency one, the fatter the time. All right, with these, you can base these plus the convolution theorem, you can basically do any Fourier transform in your head. Kind of cool. So how do we do this question that we asked here? Well, one way to do it is to do the Fourier transforms, multiply, and then do the inverse Fourier transform to get it back in time domain, right? So Fourier transform of a top hat is a sink. Fourier transform of a delta function is this thing. Multiply them together, oh God. And then we have the inverse Fourier transform, and I don't know what that means. Okay, so that one was hard. What if we didn't do it in Fourier domain? What if we did do it in time domain? Do we remember what the definition of this delta function, of the convolution is? It's sliding one past the other, right? Multiplying. Well, it turns out sliding past a delta function is kind of a friendly thing to do, because when you slide past a delta function, it's 0 everywhere except for the exact data point that overlaps where the delta function is, right? So that's actually the easier way to do it. You slide it past the delta function and it extracts the same value that is sitting on top of the delta, where the delta function spike is. So you can see that if you slide this top hat over here, you're going to get a top hat back out. And that top hat is going to be slid over to wherever the delta function is relative to 0. If the delta function is at 0, then the top hat stays where it is. If the delta function is off to the left or right, then the top hat slides. So it turns out this is the right answer. But more important than this being the answer is I wanted to talk through again what happened when we did this in Fourier domain. Remember, we took the Fourier transform of a top hat times this delta Fourier transform of a delta function. Okay, and the Fourier transform of a top hat was something complicated. It was a sink function. The Fourier transform of the delta function was a straight up sinusoid, complex sinusoid. And somehow the end of that is that this shift happens. So it turns out, and we kind of argued that I could have chosen any function over here and convolving it by a delta function. I would have gotten the same function out, just shift it, right? Which means that shifting something in time, a time shift, a translation, is multiplying your Fourier transform by a sinusoid, by a complex sinusoid. So here was the joke in the play that where they were making fun of me. The point of the play was that I was trying to avoid being chair. It was everybody was trying to avoid being chair of the department. It was like Game of Thrones, but for Game of Chairs. That was the joke. And the way I avoided becoming chair was whenever they had me cornered finally in a room, is I Fourier transformed. I did a phase shift multiplied by a sinusoid, and then an inverse Fourier transform and got out of the room so that I could not be made chair. Whether or not you think that that is a funny premise to a play is up to you. But the point to remember from it is this phase shift, this e to the I omega t, multiplying that, your Fourier transform, by an e to the I omega t, something that is changing its phase as a function of time, the way that the sinusoid does, is what a time shift is. There is a thing that you're going to do routinely in your analysis that shifts things in your NumPy arrays. And that was your FFT shift. Remember your FFT shift in NumPy that we use with your discrete Fourier transforms? Because discrete Fourier transforms, remember, were a little weird, and they put the 0 frequency at the 0 point in your array, but it put your highest frequency in the middle of the array. And then right next to it was your minimum frequency, your negative frequency. And then that went all the way up to your -1 frequency. And we said, if you want to plot this, then you kind of like your 0 to be in the middle, right? So that you could look at it and it makes sense. And we said that FFT shift was a great function that would do that for you. And I encourage you to do that. But here is the danger of FFT shift. What is it doing? It is sliding the values over your array. And we just argued that a translation, a sliding is the same thing as convolving with a delta function, which is the same thing as multiplying your Fourier transform by this weird, crazy sine wave. So if you find yourself taking a Fourier transform of something and you see this wild, fast sine wave going across the result, take a hard look at your analysis and see if you have an accidental FFT shift in it. Because that is the hallmark of an FFT shift. If you accidentally do a Fourier transform on it, you won't get your original function back. You will get a phase shifted version of your function back. Because that's what this translation does. All right. All right, so this is all a bit heavy. We're gonna have the rest of the semester to get really to the bottom of what this is, but I wanted to bring you to a key application of this, which is in mixing signals. But unlike last time, I'm gonna give us a break before we launch straight into it. Let's take a 5-minute break. Come back at 3:08. Stretch your legs, use the bathroom, do whatever you need to do. I'll take a break.
question about like the access part, because I signed up for it like over break 2 weeks ago or stuff. And I wasn't sure if I was doing the right access code because I still don't have access to the room. You know, it's like this. So that's only 17%.
Okay.
That's the only thing I would think could be wrong, but I don't know why I didn't have access yet.
So who is our new front desk person? Is it Brandy? Or no, or is Brandy, is our undergraduate resource advisor?
Randy is that.
Yeah,
it's just
yeah.
there.
Um,
But normally when I do access to stuff by emailing,
Anthony. Recon?
yeah.
Didn't he get promoted though? Don't we have a new person? It's so impossible to keep track of who's
Yeah,
doing what. Um,
I can just submit it again.
I think that might be a good approach. Another option is when I'm in doubt on something like this, I email Maria Keys, our department manager, and because I'm bad at keeping track of who's who.
Okay, I keep it around.
Yeah, you know, Maria's is like MPs. She can definitely get to the bottom of it.
Okay.
You have another 2-hour lecture?
Yeah, I have one right before this, so.
Oh, man.
4th hour.
Oh, I'm sorry. That's right.
The answer is all,
Uh-huh.
but it's afterwards.
You can ask a question of any size.
Yeah, so I do research with like power spectra and correlation function. cosmology.
Yeah.
I was just curious, like when you say a correlation in this class, is that at all the same? Like when I think of correlation, I think of the correlation function, like 2-1 correlation,
Uh-huh.
3 and so on.
Yeah.
They're not the same thing.
No, they're the same thing.
They are.
Yeah.
Yeah.
If you want to correlate two 3-dimensional volumes, do 2 3-dimensional Fourier transforms and multiply.
Wait. Wait, you said you just do. Yeah, can you say that sentence one more time?
Yeah, if you want to do a 3-dimensional correlation function between two 3-dimensional fields,
Right.
you would take the Fourier transform, 3-dimensional Fourier transform of each one and multiply their spectra. Or if you want to do a correlate, you would conjugate the spectra. But then you multiply, then inverse Fourier transform, and there's your correlation function. Yeah, no, it's the same stuff.
That's really cool. I'm gonna need that to sit with that for a second. But like, I know that like, I knew it was like, it's probably the same thing, but I wasn't sure if it's like, there's different definitions. Yeah.
There are, cosmology, I will warn you, uses a different normalization convention than,
Yeah, because I'm used to like the point estimator definition of like point correlation function, and then just taking an FT of that to get your power spectra, bispectra, et cetera. But like, yeah.
yeah, no, but it's the same stuff. All right, I think it's time for us to get started here again. Maybe some people are still out there. Let's start with one more question, one more convolution to do. Suppose I gave you a sine wave and a fast sine wave. Now, last time I think we tried to convolve these. I'm not going to convolve them. I'm going to multiply them. I'm also going to open this door. So I got these 2 sine waves, but instead of convolving them, I'm going to just straight up multiply them. And then suppose I do that, and then I take the Fourier transform. What does the Fourier transform of the product of two sine waves look like? Is the essence of my question. And I'm going to give you, as usual, 4 different options here. First one is a single spike in the center at 0. Option B is 2 spikes symmetric around 0. Option C is 4 spikes centered around 0. And option D is 4 spikes of different sizes centered around 0. Those are your 4 options. I'm taking 2 sine waves, I'm multiplying them together, and taking the Fourier transform. Right, and those of you online are welcome to enter your responses as well.
Are the 2 original sine waves same amplitude, just frequency?
Same amplitude, different frequency. Okay. Hopefully we're close to having an answer. If not, get it in. Got like 3 more seconds. And we'll end the poll. And how about in class? Got some 3s, maybe some 4s, a 2. Similarly, online, we have a preponderance of C's, a couple 4s, ones at A's or B's. Okay, so how do we think our way through this? Well, so we're in Fourier domain, so we definitely need to do a Fourier transform. What's the Fourier transform of one of these signals? What's the Fourier transform of a straight up real valued sine wave? 2 delta functions, one at a positive frequency, one at a negative frequency. Okay? So it seems unlikely that B is going to be the answer because that's the Fourier transform of just one of the sine waves, right? And it ignores the fact that we did this multiplication. So it's not that. What's the Fourier transform of a of this higher frequency sine wave? Same thing, but the spikes are farther apart, right? We'll call this new 0, frequency 0, and call this frequency 1 for frequency 0, frequency 1. And now what are we going to do with these 2 spectra? We are going to convolve them, right? You multiply in one domain, it's convolution in the other domain, and vice versa. Convolution in one domain is the multiplication of the other domain. If we multiply in time domain, we convolve in frequency domain. So we need to convolve these. How do you convolve to these spiky functions? Well, remember what a convolution is. It's sliding one past the other, and when they overlap, you take the product and integrate it, right? And spikes are actually quite easy for doing these convolutions with because most of the time, zeros are lining up with zeros and you don't get anything. The only case where you do get something is when the spikes line up, right? So if I take this, one way is if I'm sliding this left one by this right one, I've got these 2 spikes. As it comes along, first the right-hand spike could overlap this one. That'll give me 1 spike. Then as I bring it over, that right-handed spike is going to hit this spike over here and give me another spike. And then as I keep going over, the left-handed spike will overlap this one, and it'll give me a spike. And then as I go all the way over, the left-handed spike will overlap the right-handed spike, and I'll get another spike. So I need 4 spikes. So I can rule out A and B. And it's a question of whether it's C or D. And that has to do with how high these spikes are. How high are these spikes? Are they the same height? Well, it turns out the height of these spikes is encoding the power of the Fourier transform, the amplitude of the sine wave, right? So these were approximately equal in amplitude, so that's what gives us answer C here. Let's look at exactly where these spikes line up, though. As we're sliding one past the other, so we had where omega 1 hits omega 0, but we had to slide it way over. How far did we have to slide it over so that a positive omega 1 overlaps in negative omega 0? We had to slide it over at minus omega 1 minus omega 0, right? Both of them. Where it lines up here is where this omega 1 lines up with this omega 0, which is the difference between the two, right? So that would be, let me see, is it minus omega 1 plus omega 0? Or is it omega 0 minus omega 1? Omega 1 is bigger. So I think it's, yeah, I'll write it this way. Omega 0 minus omega 1, which would be a negative value. Then as we go over, then I need to make this omega 1 line up with this omega 0 right here, which turns this into an omega 1 minus omega 0. And then finally over here, we have omega 1 plus omega 0. So that's where all the spikes end up. Okay? Now, there's a really super cool thing that you can do here, which is that if you fix one of the amplitude of this, suppose we made omega, suppose we wanted to get the information of omega 1. And we, like omega 1 was a super fast sine wave, okay? And suppose I want to digitize it. But I can't sample fast enough to get 2 samples per period. And I'm really worried about aliasing. Okay? Is there a way I could do it without aliasing? Well, it turns out what we've just done here is kind of a clever way of almost being able to get there. If I generate this sine wave, if I generate omega 1 and I use it with an amplitude of 1, so I know the height of that spike, and it's well controlled, then it turns out I get this whole field right here, right? And I get the information that is the amplitude of omega 1, and I get it in 4 different spikes, one at the sum of the 2 frequencies and one at the difference of the 2 frequencies. Okay? Now, if I could make myself a filter, I made myself a nice little filter here, a nice little blue filter, and I made a filter that only let through these frequencies and blocked out these frequencies. What would I have left over? I would have 2 spikes, one at omega 1 minus omega 0, and one at the exact negative of that, right? And what is, if I took that Fourier transform back into time domain, what does that look like? It's a sine wave. It's a real valued sine wave. And what is the frequency? It's at the difference frequency. By the way, how do I do a how do I multiply by a square wave, a top half, if you will? How do I multiply by a top half in the frequency domain? you convolve with the sync function in the time domain. So that's why that's a handy one to know. Not because we have so many top hats sitting around the time domain, but because we often have a filter that we'd like to be a top hat in frequency domain, and we know now how to do it. Suppose you have some digitized data. You can take the Fourier transform of it. Do you want to filter it? Sure. How do you do it? Turns out you have two options for how to do it. One is Fourier transform it and then just multiply it by like ones where you want the data and zeros where you don't want the data. You could do that. Or you could take the time domain data and convolve it by a sync function and then Fourier transform. So you're definitely going to experiment with this in week 2. There are, for example, options like you can use numpy.convolve. There's also numpy.correlate. It does exactly what you'd think they would do. You can also take a numpy.fft because FFT is a module, and then there's a function FFT inside it, of some function. You can do it for G as well. You can multiply it, and then you can do numpy.fft.ifft to do the inverse of F. Sometimes I use underscores to do Fourier transforms. Underscore G is equal to that. Underscore F times underscore G. That's another way of writing a convolution, right? Take 2 Fourier transforms, multiply them, inverse Fourier transform. So one of the things you can do in the lab is do this Fourier transform. You can do this filtering. And then what you're going to do is you're going to learn how to do this. This is called down conversion. Conversino, down conversion. The process of down conversion is multiplying by a sine wave and then filtering. So down conversion is multiply by sine wave and then filter. And it's super useful because you can use it to get really high frequency signals down at low frequency signals that you can then sample. Like we've got a sampler over here, this Pico sampler that can sample at 62.5 megahertz, which is pretty fast, but it's not like crazy fast. We've got, if you're using your Raspberry Pis in these SDR modules, the samplers inside them are actually at, you can set their sample rate, right? And it's at like, you can set up to like 2 megahertz or 3 megahertz, 2.2, I think. You know, it's reasonably fast. It's not like crazy fast. So how the heck are we going to use these things to measure hydrogen using a telescope on our roof that is getting signals at 1,420 megahertz? Seems almost hopeless, right? There's no way, like it's going to be alias so many crazy times and all whatever, it'd be hard to do. But this down conversion is just the ticket. I've got a cool little module here. It's called a mixer. This is a, you guys can see it online here. It's a ZFM15. ZFM15. Turns out all these components, if you look at their, you just look at that thing up online, you can get a data sheet for this thing. It's kind of cool. What is a mixer? A mixer is a multiplier. It is a electrical multiplier. You put in one signal into the L, one signal into the R, and out of the I comes the product of the two. If you're interested in what that circuit looks like and you've done some some little component, you did like a little electronics course or something, it actually is pretty straightforward. It looks like a, how do I draw this? Has anybody ever done like a rectifier in your electronics class, a full wave rectifier? Then you've built a mixer before. So you use these cute little things called diodes that only allow current to flow in one direction. And you can build a little circuit that goes like this. And then you put in one signal onto this side and another signal onto this side. And then the output, I think, is, there are a little couple details that I need to put in here that are using a transformer, which are just 2 coils of wire. And then you connect the center of this one to ground, connect the center of this one. That's one of your outputs. And then the other output is I think this coil here. Anyway, at the core of it is these little diodes that only let current go in one direction. And you can kind of map out that if you put in like positive signals on one side and a negative signal on the other, that current will flow a particular direction. And you just map out all the different combinations. You'll convince yourself that coming out of this thing is the product of 2 sine waves. And it turns out diodes are just transistors, which means that these things are dead easy to build. Pretty cheap to buy, certainly a lot cheaper than buying a really expensive, fast digitizer. So you can take one of these things and you can put in a sine wave that you know. You can take a signal from somewhere else that you would like to sample, and then you can get the difference frequency and the sum frequency out of here. Yeah.
How would you add the sync function for limited?
So there are, it turns out, a lot of components that will do this for you. Usually, you don't manually specify the sync function. Usually, that what we do is take delayed copies of a signal, and you can combine them in different ways to get the filters that you want. And this, for example, I'll show online. This is what's called a low-pass filter, which is a version of that. Yeah, and so you can just buy analog filters. So you can do filtering digitally with what by doing Fourier transforms and multiplying, or by doing convolutions. On the software-defined radio module that you plug in, they actually have a thing that does a convolution directly called an FIR filter. And the FIR is like finite impulse response. But under the hood, what it actually is a convolution. It's just a straight up convolution where you tell it what each number is of the function. It slides the function. It's pretty cool. So there are ways of doing that digitally in digital electronics. There's analog versions of it. And then there's you digitize it and have it on a computer, and you can analyze it there. You can do all these things. And you can do filtering in any of these domains. And it kind of all ends up being equivalent. Although sometimes it makes more sense, for example, if you're trying to sample, you would prefer to do a filter in the analog before you sample, okay, so you don't alias things. So there are cool things like this. And if you're wondering how the hell do you build a low-pass filter, well, Frank just built us a low-pass filter for use with our noise generator. Because for example, we didn't have a low-pass filter that was narrow enough to do the software-defined radio modules that you guys have. So we had to build a new one in this class. And if you look carefully at what is on this board, which you can't see, is there a way to just show myself? Can I just look at me? No. Yeah, okay, there we go. So check out this little board right here, although it's mirrored because I guess people don't like looking at unmirrored versions of themselves because they're used to seeing themselves in the mirror. Is that why we do this? I don't know. Oh, okay, great. If you look at what these components are, these are capacitors. These are resistors. And it turns out a pretty cool, straightforward filter is to take your signal in, run it through either a capacitor or a resistor, put it into another capacitor or resistor, the opposite of whatever the first one is, and then halfway in between, at the junction between them, you take the output signal. It's what's called an RC filter. R for the resistor, C for the capacitor, an RC filter. Do you ever do a thing in like electronic, your E&M or electronics class where you have like an RC circuit and you flip it and then you watch it decay? And there's a certain time constant for it to decay. Because it takes a little time for the current to run out of the capacitor through a resistor. And that time constant is allowing you to delay a signal, to slow it down. And that's exactly what these RC filters are going to do. In a little bit, once we start talking about termination, which we will for lab number 2, I'll be able to tell you in detail how an RC filter works, which is pretty cool. So that's where we're going to leave it. Convolutions, correlations, and we're starting the idea now that we understand that they are just products in Fourier domain. We're introducing the idea that a mixer, a multiplier, can be used to shift frequencies and filter them out, which we will use to our advantage to be able to measure hydrogen with cheap electronics. All right, remember on Thursday, you guys are presenting and telling me all the cool things you've learned about aliasing and stuff like that. And thanks for joining us.